Hi everyone, welcome to Integral Calculus. Today we explore lesson 8.4, applications to economics and biology. Number one, application to economics. Consumer surplus refer to the difference between what a consumer is willing to pay and what a consumer actually pays for a product. Producer surplus is the difference between the market price and the lowest price a producer is willing to sell a product. Now let's take a look at the graph here. We have unit and price per unit, px, and x is quantity. It's the price per unit. Demand curve is the downhill slope. Demand. Supply curve is an uphill slope. They have an intersection. The intersection is called the market price or equilibrium. So we have a P star and X star. You can see there are two regions very clearly. This region right here, the area of this region below the demand and above the equilibrium price is called the consumer surplus. The other region below the equilibrium price and above the supply is called the producer surplus. It is very important to study consumer surplus and producer surplus, in particularly consumer surplus, because the area represents the benefit that the consumer get by paying less than what they are willing to pay. This means that they are more likely to buy again. Okay. From here, we can see that producer surplus, right? It would be the integral from 0 to x star of p star minus sx dx, and consumer surplus is the integral from 0 to x star dx minus p star times dx. Yeah, pretty cool, huh? Let's do an example. Example, the demand for a certain product is dx equal to 20 minus 0.05x, and the supply for that product is sx equal to 2 plus 0.002 x squared. Find the equilibrium price and the quantity. Find the consumer surplus and producer surplus. So here come x, here come px. Demand start from 20 and it's gonna go downhill. Supply start from $2 and it's the parabola, so it go up. The intersection is the equilibrium point. Okay. So in A, we want to set them equal to each other. dx equal sx. 20 minus 0.05 x equal 2 plus 0.002 x squared. Move everything to one side and we have 0 is the 0.002 x squared plus 0.05 x minus 18 divided by 0.002. We have 0 equal x squared plus 250x minus 90,000. And we can factor this out to be x minus 200, x plus 450. Because quantity cannot be negative, x equal 200 is the equilibrium quantity. And then as for the equilibrium price, we can sub it into either function. I'm gonna sub it into the demand function here. P is D of 200, 20 minus 0.05 times 200, and that gives us 10. Okay. From here, we can figure out the consumer surplus and producer surplus. B. Consumer surplus is the area below the demand curve and above the equilibrium price. So integral from 0 to 200. Demand is the 20 minus 0.05 x equilibrium price 10 dx. So this would be a negative 0.05 times x over 2 plus 10x. Evaluate from 0 to 200. So this would give us exactly $1,000. As for the producer surplus, it would be the area below the equilibrium price and above the supply curve. So integration from 0 to 200. 10 minus 2 plus 0.002 x squared dx. So this would be a ax minus 0.002 x3 over 3. Evaluate this from 0 to 200. And we get $1,006.67. Pretty cool. Let's move on to application in biology. Consider blood flows in an artery or blood vessel. An artery is a tube of length L, as in the picture, and a radius bigger R. The blood flows with velocity VR. What the greatest flow near the center of the tube, and the flow decreases as to 0 as it gets near the wall. There's a law for laminar flow. And that law say the velocity is P over 4NL R square minus the small r square. Just where N is the viscosity of blood. P is the pressure difference between the ends of the tube. The capital R is the radius of the tube. L is the length of the tube. And the smaller radius is in the interval from 0 to R. This notation has in or belong to. We are interested in how to compute the rate of blood flow, the flux or the discharge, which is the volume of blood per unit of time in the tube, because proper circulation is the key to maintaining optimal health. So now let's take a look at the tube. We see that flux varies because velocity is fastest at the center and slow down to 0 when the blood is near the wall. Using this fact, we can cut out the tube into different shells to do the approximation. Let's take a look at one shell. This one. So we will take a look at this shell, then we see that, yeah, we have a velocity, VR. The height is already in the velocity. We have a radius, right at the center of the flow, it's R. And then we also have a thickness, small change in R. So a sample flux would be flux is the unit is volume of blood per unit of time. So that is the cubic centimeter over second. So it makes sense for the sample flux to be area of the shell multiplied to velocity. The area of the shell is the circumference, 2 pi r, multiplied to the thickness, dr. And then the velocity is vr. Right? Area unit is square centimeter. Velocity is centimeter per second. So multiply them together, we have cubic centimeter per second. 2 pi r dr, and the velocity from law of laminar flow is P over 4NL. The bigger R square minus the small r square. We have pi P over 2NL. R square times small r minus r to the power 3 dr. The flux would be the integral from 0 to r, because we have to add up all of these shell of a sample flux pi p over 2nl r square times r minus r to the 3 dr, right? Pi p over 2nl r square times r square over 2 minus r4 over 4. Evaluate from 0 to r. What we have is the pi p over 2nl. This is r4 over 2 minus r4 over 4. Simplify this and we have pi p r to the 4 over a and l. Okay, so what is so cool about the flux here is that if you look at the radius, right, it's r to the 4. So it has the biggest effect on the flux. The flux is very sensitive to the vessel, blood vessel diameter. And this is a very cool result because it does give an explanation of the high blood pressure. Small diameter result in a less blood flow. It leads to high blood pressure. Thank you for watching. I hope you find the content useful. Please like, subscribe to help the channel grow. I will see you in the next video.